Welcome back everyone. In the previous lecture video, we made an analysis of the geared system and we learned how to convert this geared system into equivalent 2-rotor or 3-rotor system. So in this video, we'll be solving a problem from this same topic. So before that, I would like to make a revision to know the equations which are required to solve the problems. So in geared system, two shafts will be there. One is the main shaft and another one is the geared shaft, and both are connected by a pinion and gear or this two gear arrangement. The two main rotors are the rotor A and rotor B, and this will be forming a 2-rotor system if the inertia of these gear elements are neglected, and if you are considering the inertia of these gear elements, that is this combination also, then you will be having 3-rotor. That means it will be forming a 3-rotor system. So this is the equivalent 2-rotor system and this is the equivalent 3-rotor system. In both of this one, we will be keeping the first section same. That means the main shaft of diameter dA and length L1 with this rotor IA moment of inertia will be kept constant. And the second part will be considered, which is equivalent from this geared system. So in geared system, the one which is coming in the geared shaft, which is of diameter dB and length L2 with mass moment of inertia IB, will be taken. In a 2-rotor system, this will be neglected. Then this L2 will be becoming L2 dash, and we will be finding, or we are having an expression for this L2 dash here, where GR square into L2 into dA by dB the whole raised to 4 is coming. All these discussions were made in this previous video, where GR is the gear ratio. So you can define the gear ratio as the omega angular velocity of this pinion or the first main shaft divided by omega B. So this is the omega A and this is the omega B. So this ratio is known as gear ratio, and we will be making modifications or corrections to the mass moment of inertia of rotor IB. Then it will be becoming IB dash, and that equation is IB dash is equal to IB divided by GR square. And in the case of a 3-rotor system where you are taking the inertia of this gear element, then it will be becoming only the change in addition to L2 dash and IB dash is the IC dash, and the IC dash value is equal to ICA, where it is the mass moment of inertia of this gear which is coming on this main shaft, that is the pinion. The smaller one will be known as pinion and the larger gear will be known as the gear wheel. So this ICA will be of this mass moment of inertia as this one plus ICB, that means this gear divided by GR square. So these substitutions will be requiring for converting the geared system into an equivalent 2 or 3-rotor system. With this one, we will be seeing the problem now. So in this problem, a reciprocating IC engine is coupled to a centrifugal pump through a pair of gears. So these are the pair of gears which are coming. Here the engine flywheel is connected to the main shaft. The main shaft is of 48 mm diameter with 800 mm length, and this 800 mm will be calling it as L1 and 48 mm will be our dA, and this engine flywheel is having a mass moment of inertia of 1000 kg meter square. That is actually given in this question. And this gear is connected to the pinion, and this pinion is connected to the geared shaft, which is at the end of which the pump is coming. So here the larger one, the gear wheel will be coming here, and the smaller one, that is pinion, will be coming here. So the smaller gear will be rotating at higher speed. So if you are calling the speed of this one as omega B and this is omega A, it is given that pump speed is 4 times the engine speed. That is, you can write it as omega B is equal to 4 times omega A, where B is coming on the pump side and A is coming on the engine flywheel. So here you can find the constant or the gear ratio, so-called gear ratio, which is equal to omega A divided by omega B. And here the value of gear ratio will be equal to 1 by 4. And this will be substituting in this further equations. And here it is given that the shaft portion, that is the geared shaft L2 is of 280 mm length and its diameter is 32 mm. So from this geared system, we will be forming a 3-rotor system, because here all the mass moment of inertia of this rotor A, the gear, you can call it as ICA, and this pinion ICB by 5 kg meter square, and this IB, the main rotor at the pump, is also given. So here, since this inertia elements are given, you can consider or construct a rotor out of this one to form a 3 rotor system. Then this section will be kept as such. So that means here we will be having length of L1 which is equal to 800 mm, diameter is 48 mm, and this IA will be same as 1000 kilogram meter square. Then you will be having this rotor IC which is corresponding to the gear elements. So you have to calculate this IC dash. So you are having the equation that we'll be evaluating now, and this much part, that is 280 mm. Part of diameter 32 mm. So you will be making or maintaining this 48 mm diameter constant. So this dB 32 will be becoming dB dash which is equal to dA of 48 mm. Then the change will be occurring for L2 and this mass moment of inertia IB. That means L2 will be becoming L2 dash and IB will be becoming IB dash. So the things which you have to evaluate are, one is L2 dash, one is IB dash, and another one is IC dash. So first we will be calculating the L2 dash. The equation for L2 dash is equal to GR square into L2 into dA divided by dB the whole raised to 4. This equation I have shown just before and it is also discussed in the previous video. So GR is 1/4 which is equal to 0.25 square into L2 is 280 mm in actual geared system. So this will be becoming, what we are evaluating is coming in the 3 rotor system, into dA is 48 and dB in the geared system for the second part is 32. So this much raised to 4 will be coming. So if you are evaluating at the end, this L2 will be becoming in mm you will be obtaining. So this L2 will be becoming 88.6 mm. So in the 3 rotor system, this L2 dash will be 88.6 mm. In a similar way, you will be evaluating the IB dash. The equation for IB dash is equal to IB divided by GR square. This IB is equal to 18 kilogram meter square divided by GR square is 0.25 square. And then this IB dash will be becoming 288 kilogram meter square. So this is the change in value for this mass moment of inertia of rotor at the pump location. And similarly, you will be evaluating the IC dash also. So IC dash expression you are having, IC dash is equal to ICA plus ICB divided by GR square. This ICA value is given in the question, which is 14. This ICB is 5. And this GR is 0.25. So 0.25 square will be coming. And finally, you will be getting the expression for IC dash, which is 94 kilogram meter square. So now you have reduced the geared system into a 3 rotor system where the mass moment of inertia of the rotors are IA equal to same 1000 kilogram meter square, IC dash which we evaluated now 94 kilogram meter square, and the final one is IB dash which is 288 kilogram meter square. And the length of the shaft L1 equal to this much length is 800 mm which we are keeping this as same, and the second part equivalent length L2 dash is 88.6 mm with a uniform diameter of 48 mm throughout the shaft. So this 3 rotor system we will be solving as usual as in the previous videos. Then we will be finding the frequencies, that is we will be calculating the 2 node frequency and the single node frequency. So you are knowing about the 2 node and 3 single node frequency. So first we will be formulating the equation based on the 2 node frequency system. Then you can find the frequencies for this 2 node as well as single node case. So in the 2 node means there will be 2 node points within the system. So let us, this is representing that case. So where the rotor A and rotor B will be rotating in the same direction and this rotor C will be rotating in the opposite direction in such a way that 2 nodes are formed. And the location of the first node with respect to this A will be designated by LA, and the second node with respect to B will be represented by LB dash. And in between these two lengths LC1 and LC2 are coming. This we have already studied, and this much length, total length is L1, and that is 800 mm you are knowing. So L1 will be the sum of this LA plus LC1, that is coming here, and this total length L2 dash is 88.6 mm which is the sum of this LC2 and this LB dash. So with respect to these 2 node points, you can form or convert this 3 rotor system into 3 equivalent rotor system that we have discussed earlier. and based on those system you can equate the different frequencies of those three single rotors. Then you can formulate or find these lengths LA and LB dash. So for that, first you will be taking this rotor, and then you will be taking this rotor, then you will be equating. Then you are having the condition which you are already studied, which is LA into IA, this much length LA into mass moment of inertia IA is equal to this much length LB dash into IB. So this LA and LB dash are unknown. Anyway, you are knowing the values of IA and IB. So you can formulate an equation or connection between this LA and LB dash from this one. So if you are substituting the value of this IA equal to 1000 and IB dash is equal to 288, then you will be getting a connection between this one, that is LB dash is equal to 3.47 LA you will be getting. And in the next case, you will be equating the two rotors, which are, one is this single rotor which is containing this LA and IA, and the another rotor between these two nodes, that is this including this L1, LC1, LC2 and this rotor of having magnitude IC or IC dash. So for that case, you can write 1 by LA into IA is equal to 1 by IC dash into 1 by LC1 plus 1 by LC2. This we already studied. And here LC1 you can represent in terms of L1 and LA, where L1 is the non-value or constant 800 mm, and LA you are evaluating here. So LC1 is L1 minus LA, and in a similar way, this much length LC2 is this L2 dash minus LB dash. And in this one, L2 dash is 88.6 mm, and this LB dash now you can represent in terms of 3.47 LA. That means finally in this equation, the only unknown will be LA. So you can solve for LA as it is a forming a quadratic equation. This LA will be having two values, and those two values are, in one case LA you will be getting as 0.059 meter if you are substituting all units in SI units, or it is 0.0059, or it is 5.9 mm. This is the one value, and the next value is 0.2354 meter, or it is the 235.4 mm. And corresponding to these two values, you will be evaluating this LB dash. So LB dash is equal to 3.47 into LA. Then one value will be getting as 0.0204 meter, that is 20.4 mm. You will be getting one value, and corresponding to this one, LB dash will be equal to 3.47 into 0.2354. Then you will be getting value of 0.817 meter. This is equivalent to 817 mm. So one pair of these values of LA and LB, that means this pair will be giving you one case, that it will be giving you the 2-node frequency, and this pair of LA and LB dash will be giving you the single node or the fundamental frequency. So with this system, you can evaluate the values of the natural frequency of, or the natural single node as well as 2-node frequency. So the system which is shown here is representing the 2-node case. Then after solving this LA value of 5.9 mm will be representing this much length, and this 20.4 mm will be representing this much case. So here anyway, this LA is lesser than L1. L1 is 800 mm and this is just 5.9 mm. So that is coming within this section. And similarly, LB dash we have obtained as for this combination 20.4 mm, and that is much lesser than this L2 dash, so 88.6 mm. So in this case, both will be coming in this position, so that it is representing a 2-node case. So for this one, you can evaluate the 2-node frequency. So the 2-node frequency you can evaluate using this expression, square root of Q divided by I. So QA divided by IA you can evaluate, where this QA is equal to G into J into A divided by LA into IA. So here you can take the rigidity modulus as 84 gigapascal. So it is 84 into 9, and JA is pi by 32 into D raised to 4. Here it is 48 mm. So it is 0.048 raised to 4. All values we are substituting in SI units, divided by LA. Here LA value is 5.9 mm or 0.0059 meter, into IA value is 1000 kilogram meter square, that is also the SI unit. Then you will be getting the 2-node frequency, and finally you will be getting the answer as 84.19 radians per second. So this is the answer for the 2-node frequency. And next way, using this pair of values for this LA and LB dash, you will be calculating the single node or fundamental frequency. So the case for fundamental frequency, which is corresponding to the other pair of values of LA and LB dash, is given here. So in the second case, the value of LA you have obtained it as 235.4 mm and the LB dash value was 817 mm. So here in actually L2 dash, this L2 dash is only 88.6 mm. So this 817 is coming in the next side. So this will be formulating an imaginary node where you are getting from this extension of this amplitude from these two rotors. So here the rotor A, rotor C, rotor B. So here rotor B and C are rotating in the same direction and A is rotating in the opposite direction. So the actual node is coming within the system because this LA length, the 235.4 is lesser than this 800 mm, but here this 817 is greater than 88.67, so which is forming an imaginary node. So here also you can evaluate the natural frequency corresponding to the single node using this equation. So here the actual node is coming here. So with respect to this one, you can take this part, so that is of LA and IA. So for this part you can evaluate the torsional stiffness QA, then the natural frequency of the single node system. So single node, I will be calling it as omega n1. So here also you can use G into JA divided by LA into IA. So here only the difference is for LA, where LA value is 235.4 mm, or in SI unit it is 0.2354 meter. All other values are similar to the previous one. So at the end of this substitution, you will be getting the single node frequency as 13.32 radians per second. So this is the complete solution for this torsional vibration of geared system. The first step was to convert the geared system into 2 or 3 rotor system, where you are modifying the length of the second part, moment of inertia of the second rotor, that is IB to IB dash, and also if you are considering the moment of inertia geared elements, then you are calculating the IC dash. Then using that conventions for the 3 rotor system, then you will be finding the 2 node frequency and single node frequency, and also you can locate the node. So this is the way to solve this geared system problem from this torsional vibrations of geared system. So this is also somewhat tricky. You will have to invest more time on this to understand. So anyway, hope you understood, and thanks for watching.